Here comes another definition. Given a set, actually a collection, C, of subsets of omega, so C is a subset of the power set, the sigma algebra generated by C, which we write as written sigma C, is the smallest sigma algebra that contains C. The smallest sigma algebra containing C. So, smallest, put that in quotes. That's mathematician speak for, so that is sigma C, the sigma algebra generated by C, equals the intersection over all sigma algebras containing C. So here A is a sigma algebra. All the sigma algebras containing C of those sigma algebras. So when mathematicians say it's the smallest something containing something, this is what they mean. It's the intersection of all of those things that contain it. Now, there's something a little bit fishy about what I just did, because there's no reason to believe that this thing even exists. I said the sigma algebra, the smallest sigma algebra containing C, but who's to say that there even is such a thing? Well, there is, in fact, and here is why. So here's a remark. Sigma C always exists because two facts. First, the power set of omega is itself a sigma algebra. Always, for any omega. And two, any intersection of sigma algebras is also a sigma algebra. So these are two facts which I claim are true, and you could prove them. These are pretty straightforward exercises. Something, if you're interested in measure theory, then you may want to sit down and write out a formal proof of these. But these two, which I claim are true, imply that this always exists, because the first one implies that this intersection is non-empty, because there's always, so the power set always contains this collection C, so this is a non-empty intersection. And since the intersection of any collection of sigma algebras is itself a sigma algebra, then this intersection is a sigma algebra. So this definition makes sense. That's what the remark is saying. Let's look at a couple examples of sigma algebras. So here's a first example. Nice and simple one. The simplest one, actually. The trivial sigma algebra. So just take the empty set, take the whole space omega. That's a sigma algebra. Here's another example. Also pretty trivial. Take the empty set, take any set E, take its complement, and take the whole space. You can prove that these are sigma algebras if you want. So here's a third example. Now this one, these were pretty simple, but this one is important and complicated. Not complicated to understand, but the thing itself is a beast. So here it is. If omega is the real numbers, the Borel sigma algebra this is a definition, is the sigma algebra which we denote by script B, and it's equal to the sigma algebra generated by all the open sets of R. So T here is all the open sets. Now, what the heck is an open set? If you don't know topology, then this is meaningless to you. An open set is, so for example, an interval like, so set aside, just to give you a sense, if you don't know topology, it's an interval like any numbers a and b. Open interval is an open set, or any union of these is an open set. So the Borel sigma algebra is the sigma algebra generated by the open sets of R. And more generally, if omega is any topological space, then the Borel sigma algebra for that topological space is defined in the same way. Now we come to measures. So let's make some space here. This is important. This is good stuff. So here's another definition coming at you. A measure, mu, on omega with sigma algebra A is a function. It's a function on sets. So it's a function mu from this collection, this sigma algebra, to numbers from 0 to infinity. And in fact, we allow it to take the value infinity, such that two conditions hold. First, this measure, this function evaluated on the empty set must be 0. And second, this function evaluated on a union, a countable union, of disjoint sets, pairwise disjoint sets, equals the sum of that union. So for any sequence E1, E2, E3, etc. in our sigma algebra, if they're pairwise disjoint, then this condition must hold. And this is called, condition 2 is called countable additivity. So that's the definition of a measure. And let me give you one last definition for this video. all important for us, a probability measure is a measure P with the condition that P of omega equals 1. So it's a measure P. I'm writing P instead of mu here. It satisfies all these conditions, and further, it satisfies that P evaluated on the whole set omega equals 1. So let's stop there, and next time we'll take a further look at some examples of probability measures.